So now we've actually looked at the functional groups. Let's now delve into the chemistry of these functional groups. So we're going to look at essentially 6 major functional groups and the chemistry they undergo: the alkanes, the alkenes, benzene, alcohols, halogen alkanes, and polymers, which are related to basically most of them. So in terms of the learning objectives, I've outlined them each individually for each of the different functional groups, and we're just going to go through those step by step. Essentially, it involves understanding what reactions each functional group can undergo, and also writing equations around that, and some explanations of why certain functional groups react in certain ways. The first thing before we start looking at the reactions is looking at some conventions about writing reactions. So a double barbed arrow, like this one here, okay, indicates the movement of an electron pair, okay. So because it's a double barb, it means you've got an electron pair, so 2 electrons are moving. However, a single barbed arrow, as you can see here, indicates the movement of a single electron. A single large dot, like this right here, indicates a radical. Okay, so it's an atom which has this electron here. And it's not a single electron, but it's actually an incomplete valence cell. Okay, so that dot, instead of representing an individual electron, actually means there is a gap in the valence shell of that particular atom. So square brackets means the charge is distributed over a complex, okay, and we've already looked at complexes earlier in the course, and dashed lines indicate electrons are shared by more than one bond. So that's looking at the idea of your resonance forms. Okay, so now we have some conventions, we can start looking at the reactions. So in terms of organic molecules, in terms of molecules in general, they are 3-dimensional. Okay, so you might see that molecules are drawn the following way. Okay, essentially a line in the page, like here, is that it's going straight up. Okay, it's not going in or out of the page. A dashed line means it's going behind the page in 3 dimensions. And a wedge means it's coming towards you, it's out of the page. Okay, so a wedge is coming towards you and a dash is going away. So we'll start off with the alkane reactions, and examples of those are combustion reactions and photochemical substitution, also known as halogenation. Okay, so that's how we'll end up getting the halogenoalkanes. So in terms of chemical properties, alkanes have carbon in them, obviously, and only hydrogen. And an important term in terms of chemistry and organic chemistry is catenation, and it's the ability to form bonds between atoms of the same element. So obviously, in alkanes, you've got carbon-carbon bonds. Okay, so carbons can form chains or rings. We've seen the rings in terms of benzene, and single, double, and triple covalent bonds. Okay, the alkanes, the alkenes, and the alkynes, because it is able to form strong covalent bonds with other carbon atoms. So in particular for the family of alkanes, they're fairly unreactive. Okay, the old name used was paraffin, so you may have heard of paraffin wax, for example. It means that it doesn't react much, little reactivity. They have relatively strong, almost non-polar single covalent bonds, and they have no real sites to encourage nucleophiles or electrophiles to attack them. Okay, and we'll learn more about what nucleophiles and electrophiles are later. So carbon forms a vast number of carbon compounds because of the strength of the carbon-carbon single bond, this covalent bond. Other group 4 elements like silicon can do it, but the chemistry is limited because they have weak bond strength, or weaker bond strength relative to carbon. So if we look at the data, okay, you'll see that the carbon-carbon bond, the energy required to break that bond is about 348 kilojoules per mole of carbon, whereas for silicon, it's about half. Okay, the reason being is if you look at the atomic radius of carbon, which is 0.08-ish, nanometers, and silicon's about 0.1 nanometers. Because silicon is a larger atom, the weaker the bond. This is because shielding occurs due to the filled inner orbitals and a greater distance of these outer electrons from the nucleus. It means that shared electron pair is held less strongly. Okay, so it's a lot to do with the shielding and the distance from the nucleus because it's such large atoms as you go down the group. So there's two types of combustion reactions that alkanes can undergo. We have complete combustion, where the alkane reacts with oxygen to form only carbon dioxide and water, as in the first reaction we have here, or incomplete combustion, where there's an incomplete amount of oxygen, so carbon monoxide forms instead of carbon dioxide, and water forms. And chances are you might also get a little bit of elemental carbon floating about there, because it's quite a sooty flame. And there's three ways that you can split the electron pair in an unsymmetrical covalent bond. Okay, so if you have unequal splitting, okay, so where you've got a covalent bond between X and Y, and one of the atoms gets both the electrons, that produces ions, and it means that you've got a negative ion and of course a positive ion, because one atom has lost lost the electrons to the other atom, and this is known as heterolysis or heterolytic fusion. Okay, it can happen both ways. You can either get X minus or X plus ions, or Y plus or Y minus ions, depending where the electrons are unequally shared. Then you have equal splitting, known as homolytic. Okay, because they're both the same. Okay, and this produces your radicals because both of them end up with a gap in their outer electron shell. This is known as homolysis and homolytic fusion. If several bonds are present, the weakest bond is usually broken first, and energy to break the bonds can come from a variety of energy sources, either being heat or light, okay, which you may have seen last year. And in the reaction between methane and chlorine, for example, either can be used, okay. In the laboratory, we do tend to use UV light because obviously using energy with a flammable gas like methane can be dangerous. Okay, so one of the mechanisms you have to know is the free radical mechanism of the substitution reactions of alkanes, and it's a form of homolytic fusion because the substitution reaction is where electrons are shared when a bond is broken. Okay, so it's homolytic. And a free radical is formed when an atom or molecule has one free unpaired electron. Okay, so this is where the fishhook arrows come in. You'll notice they're single fishhook arrows. Okay, so for a mechanism that is to be known, okay, so you've got methane with chlorine. Okay, so the first step is you have an initiation. Okay, that usually happens in the presence of UV radiation. Energy is provided and forms two chlorine radicals. Okay, and you can see that down below with the diagram here. Okay, one electron is moving to one of the chlorines, and the other is yet moving to the other chlorine. Okay, and two radicals are created, and you'll notice that the octet rule is not being obeyed. You've got one gap in the octet, so now you've got two free radicals. So during the initiation, the weakest bond is broken as it requires less energy, and there are three possible bonds in a mixture of an alkane and chlorine. So you've got either a CH bond, which has 412 kilojoules required to break it per mole, 348 for the carbon-carbon, or 242 for the chlorine-chlorine single bond. Now obviously you can see that 242 is the lowest, so that's going to get broken first, in preference to the others because they have a very large energy associated with them, because it requires less energy to separate the atoms in chlorine. Okay, so this mechanism has to be known, so let's look at the reaction of methane and chlorine. So we'll look at initiation. So essentially what has happened is that the chlorine has been split, okay, homolytically to form your chlorine free radicals, okay, and those chlorine free radicals then interact with methane to form a methyl radical here, okay. So what's happened is that has occurred here, okay. So now the methyl radical forms. The methyl radical then gains an electron from the chlorine here to become methyl chloride, and a chlorine radical forms here, okay, because that guy has now missing an electron in its valence shell. And then this is known as propagation, okay, because that can continue on. This chlorine radical here can go back into this step here and continue on the process until the termination step. Now, in the termination step, what happens is either two chloride radicals interact to form a chlorine atom, or the chloride free radical can react with a methyl free radical to form methyl chlorine here, or chloromethane, or the two methyl radicals can interact to form ethane. And you'll notice there's no more free radicals left on this side, so it means that no more propagation can occur because there's no more free radicals, and the chain reaction has been terminated. So in terms of methane and bromine, again a mechanism that has to be known. Okay, you have homolytic fission releasing the two bromine free radicals, and again the bromine free radicals interact with methane to form the methyl free radical and a bromomethane. Okay, and this hydrogen bromine gas is a colorless gas, and it's brown to, i.e. brown to clear. Okay, so it goes from being brown because you've got bromine to clear, which is a sign that the reaction has occurred. So that's alkane reactions. Now let's move on to alkene reactions, which have this more, I guess, electron-rich double bond, which can undergo different reactions, in particular addition reactions and polymerization. So in terms of the properties of alkenes as compared to alkanes, you will know that the carbon atoms in alkenes are sp2 hybridized with an outer pi bond that is the site for reactivity, allowing a range of these new addition reactions. As the bonds in the double carbon bonds are not stable as single bonds, okay, they are energetically favorable to be converted into single bonds. Also, they have a high electron density right in the double bond, making their activation energy quite low. So an example of a reaction that alkenes undergo is the addition of hydrogen, okay, hydrogenation, which was one part of my PhD project, where you basically add hydrogen across the double bond. Okay, so we go from propene, under quite forcing conditions, to propane. Or you can have the addition of a halogen onto the double bond by reacting an alkene with a halogen, or hydrohalogen in this particular case. Okay, and you get the corresponding halogenoalkane. And this is a test for determining the difference between an alkene and an alkane. Okay, because alkenes will react with bromine water in normal conditions without need for UV light. Because remember, UV light is required to make these free radicals. The bromine water changes from brown to clear, therefore tube A must contain an alkene, okay? So this here is an alkene. You react it with tube A, react it with bromine water, and it goes clear, then you're going to get an alkene. If you react bromine water with an alkane, unless it's in UV, then you're not going to get any reaction. So in terms of addition of a halogen to an alkene, okay, the bromine is a polar molecule. Okay, you have a slightly polar, one bromine is slightly more negative than the other bromine. Okay, and what happens is the electrons of a double bond are attracted to the slightly positive bromine. Okay, and then the electrons from that slightly positive bromine move on to the slightly negative bromine, as you can see here. And notice now it's a double-headed arrow, so now 2 electrons are moving. Okay, this forms something called a Carbo Cation. Okay, it's a cation because it's positive. Okay, the reason being, of course, now you've got only 3 bonds to that carbon with that single bond formation, and then the associated bromide ion here is going to be attracted to the carbocation, so you get this double substituted product here. Okay, so just reinforcing that, an alkene with bromine water, you will see a reaction, whereas an alkane with bromine water, it will still remain brown. There's no reaction because of this particular reaction. So addition of water to an alkene, again, quite forcing conditions. Okay, so what you do is you basically react the alkene with concentrated sulfuric acid at high temperature, and what's going to happen is going to form something called an ethyl hydrogen sulfate. Well, basically a hydrogen sulfate intermediate plus water, and then that water is going to react to form the corresponding alcohol. Okay, so it basically works through a hydrogen sulfate intermediate. And then finally we have polymerization for the alkenes. So alkenes can be added together to make long polymer molecules. Here, in this example here, we have ethene as the monomer reacting to form the plastic polyethene. So in terms of the summary of the alkenes can react with hydrogen, with a transition metal catalyst usually, to form an alkane, where there's addition to hydrogen across the double bond. They'll react with a halogen, molecular halogen, to form a dihalogen alkane. Okay, and you'll see that because the change will be from brown to colorless, the brown of the bromine forming the colorless dihalogen alkane. It can react with a hydrogen halogen, HX, to form the monosubstituted halogen alkane, or can react with concentrated sulfuric acid with a little bit of water to form the corresponding alcohol. Quite useful. Then we have the alcohol reactions, which are combustion, oxidation, and esterification. So in terms of the complete combustion of alcohols, this is an extreme form of oxidation. Like all organic compounds, they give carbon dioxide and water, only in excess oxygen. And of course, if there's not excess oxygen, you're going to have incomplete combustion. They may burn more cleanly than the equivalent alkanes, okay, because you've got oxygen in the alcohol compound itself. Okay, so you get less carbon monoxide and less chance of incomplete combustion. And alcohols with longer chains have a greater molar enthalpies, but may not be able to burn as cleanly. Okay, and that's the reaction there. Basically, alcohol plus oxygen gives carbon dioxide plus water. So you can see there, as we go down the group, the number of carbon atoms increases, the amount of energy being released increases, okay, which does make sense, which is more bonds that are being broken. Okay. Now, in terms of the oxidation of alcohols, tertiary alcohols don't tend to get oxidized. That's very, very hard to do. Secondary alcohols are oxidized to ketones, and then there's no more oxidation. And then finally, primary alcohols like ethanol can be oxidized up to the aldehyde, and then can be oxidized up to the carboxylic acid. So in terms of the oxidation of primary alcohols, you can easily oxidize the primary alcohols up to aldehydes, okay, by using a simple oxidizing agent like potassium permanganate or potassium dichromate. That will form ethanol, okay. And if you wish to only get to the ethanoic acid, then you essentially distill off the aldehyde before it gets oxidized to the acid, okay. Because what's going to happen is that the ethanol or the aldehyde is going to get further oxidized by the potassium permanganate, potassium dichromate floating about into the corresponding ethanoic acid. So if you want to avoid that, you want to distill off the aldehyde as soon as it starts to form. So in terms of practice, the alcohol is dripped into a warm solution of the acidified oxidizing agent, being it potassium permanganate or potassium dichromate. You can see this because the dichromate is reduced from orange to a green color, because you now form chromium 3 plus as it has been reduced. Okay, and the purple gets reduced down, the purple Mn7 plus gets reduced down to Mn2 plus, which is colorless. Aldehydes have low boiling points, so they distill off quite quickly and quite effectively, immediately. And if you don't do that, you're going to end up with a carboxylic acid, because what's going to happen is you're just going to continue oxidizing the aldehyde up into the corresponding acid, carboxylic acid. And to oxidize the alcohol straight to the acid, you can heat it. It just speeds up the whole reaction, and there we go, we've done it. Okay. And you can see the reason why we have the high boiling points, because ethanol has hydrogen bonding. Ethanol does not have that, so its boiling point's a lot lower, whereas ethanoic acid again has hydrogen bonding, so the corresponding boiling point is a lot higher compared to the corresponding aldehyde. So in order to control the products you form with the oxidation of primary alcohols, you need to distill off the aldehyde, because it obviously has a lower boiling point because it's losing the hydrogen bonding. And if you want to get straight to the oxidation to carboxylic acids as a product, the aldehyde is then condensed back into the mixture to get oxidized to the acid, rather than fractionally distilled off. In terms of oxidation of secondary alcohols, you can oxidize those to ketones, but that's all, okay, because I'm not sure what you'd be able to oxidize that up to any further anyway. The alcohol is refluxed with an acidified oxidizing agent, usually potassium permanganate or potassium dichromate. However, if you continue the refluxing, you get a mixture of acids, and basically you're cleaving you're breaking down the product that you're trying to make, the propanone, in the example on the PowerPoint. And so you end up with a whole mixture of different weird acids that you don't want. So you want to do a quick reflux, an acidified oxidizing agent, and that should give you your associated ketone. Probably fractional distillation would be quite useful at this stage to purify off the ketone you want. And in terms of oxidation of tertiary alcohols, they don't oxidize. So then we have the esterification. Okay, so in that, the carboxylic acid plus an alcohol gives an ester plus water in an equilibrium reaction, with usually a bit of sulfuric acid or a mineral acid, a drop of concentrated mineral acid as a catalyst, as you can see from the diagram on the PowerPoint. And finally, we have the halogeno-alkane reactions, which is the nucleophilic substitution. In terms of terminology, we're introduced to the term nucleophile. Okay, so a nucleophile essentially comes from the Greek. Okay, so it's phile for loving and nucleo for positive. Okay, nucleus of an atom is positive, so it's something that likes positive. So reactants with non-bonding electron pairs that are attracted to a positive carbon, which is a form of electrophile. Okay, which electrophile meaning loving negative. Okay, so what do we mean by that? So that would be something like a bromide. Okay, so the reactants with a non-bonding electron pair that is attracted to a positive carbon. Okay, bromide, hydroxide, cyanide. Okay, those are all examples of nucleophiles. And in terms of the substitution of halogenoalkanes, it's an example of heterolytic fusion. So we have a formation of a carbo cation, okay, and we'll discuss that soon, and a negative ion due to a carbon losing its shared electron. As the carbon-halogen bond means carbon is slightly positive, halogenoalkanes are reactive and undergo nucleophilic substitution reactions from nucleophilic attack. Okay, so a carbo cation, what is that? Well, let's just use the example of bromomethane. Okay, so what happens is that bromine is electronegative, more electronegative than carbon. Okay, so this is going to be slightly positive and slightly negative. So electron density tends to form on the bromine part of the bromoalkane. So that means that the carbon, once that's been cleaved, essentially forms something called a carbo cation. Okay, and then the nucleophile can come along and attack that carbo cation that has been formed, that carbo cation intermediate, as it were. So in terms of the substitution reactions, general formula, here's an example. So Rx, where X is a halogen, plus hydroxide, okay, which is the example of the nucleophile, okay. So this guy leaves, okay, forms X minus. The hydroxide comes in and attacks, leaving ROH, the alcohol, and X minus. So an example here with sodium hydroxide. So here we have chlorobutane. It reacts with sodium hydroxide to form butanol plus sodium chloride. That's quite forcing conditions, though, that will require heating and by boiling, basically. So it's quite forcing conditions. So last one is benzene reactions. Example, electrophilic substitution. Okay, so here we have a electrophile this time instead of a nucleophile. It's positive. It's going to like electrons. So the electrons are going to be attracted to the electrophile, okay, on the carbon. Doesn't really matter which carbon you choose because it's going to be symmetrical. Okay, so the electrons here in the hydrogen carbon bond move to the electrophile, form a bond here. Okay, new bond is formed between the benzene ring and the electrophile, leaving a proton in its wake. Okay, just know electrophiles will substitute. Specific reactions do not need to be memorized, but I have memorized them. They are wonderful. But here's a couple of examples here. So this is making nitrobenzene. Okay, so you have your benzene plus nitric acid, bit of concentrated sulfuric acid, beautiful at 50 degrees, get a nice yellow compound called nitrobenzene, lovely. You keep on pushing that, you get trinitrobenzene, getting close. If you have toluene instead of benzene, you get trinitrotoluene, or TNT. Great way to make explosives, just putting it out there. Okay, and then we have another example of benzene reacting with chlorine. Very similar to my first reaction in my PhD. You use a Lewis acid like aluminium trichloride and dry ether, you're going to get the formation of chlorobenzene, which stinks. But anyway, those are just examples. You don't have to memorize those particular reactions. Okay, so that's the end of the SL component. Next stop is HL.